global tensorization. So I claim that this functional has a global tensorization if a product maximizes this. That's what we want to show. Okay. So the moment you see global, you should also interpret this must be a local thing. That's what I'm going to say. I'm claiming that a functional is said to satisfy local tensorization if the product of local maximizers of the two components is a local maximizer in the larger space. Those are a priori two different properties. One is asking whether the product of local maximizers is a local maximizer. The other is asking, is the global maximizer a product distribution? Neither imply each other a priori. But what I've seen for all the cases what we've seen is that they both hold together or never. So in some sense, either they're both global and local for the family, or both fail. So in fact, the way we found counterexamples is to first test the local tensorization, see that it fails, use that intuition about what channels will global tensorization, and that's how we got the intuition. Okay. Second derivative, first and second derivative. Yes, at this point. I mean, though when I'm going next step, I will be more picky, because there are cases where second derivative is also 0, so you will have to look at higher derivatives. Yes. I need maximizer, I need concavity, but there may be some directions where it's too flat that you may not even have concavity, and there are cases where usually fourth derivative, because fourth derivative has sign or something like third derivative should be 0 and fourth. So in the BEC, that's why I said BEC is more interesting, because you get the fourth derivative, even for the hypercontractivity. But it's still a local max, it's still a local property. Oh, usually except for some points, that local test is usually a LMI, linear matrix inequality. You want to test a property of the form summation, so you want to test so you will have tests like summation alpha I, AI, these are all PSD matrices. They'll be bigger than or equal to summation beta k bk, say 1, or j equal to 1 and 2, and you want to see whether this implies, whether does it imply that summation alpha I so that's local tensorization will essentially reduce to testing something like this. Though it's not exactly equivalent to testing this, because these matrices must come from these distributions. So they are not only PSD, they are also all the entries are non-negative. So they are non-negative PSD, but it's actually even a subset of that. Okay, so there may be violations where they are PSD, but they cannot be realized from this. Right. So one has, but it will be of this. Okay, so but this is easy. I mean, once you have this is easy to test. So this is the kind of local test. So it's not local test is not very, very hard, because you know these matrices. Okay. So okay, if you Google search local tensor, okay, now what is the last point I'm saying? I'm saying that so it's similar to asking if this condition is true, then you have a local condition to test. To show. If you Google search global tensorization and local tensorization, you will get a reference, at least a few references, and that refers again work in differential geometry. They look at entropy flows, and they have some kind of curvature dimension condition which also has some kind of property like this, but that is similar to convexity. So they don't yet come to non-convex problems yet, but they come near convexity. So this phenomenon has been observed in some other fields, but it's not yet come to the point where we can pick and use it. Okay. So for some of the problems, for instance, for Martin's inner bound for binary input channels, we can verify local tensorization. For the Gaussian Z differential channels, we can also verify local tensorization. We can prove that locally tensorized. So if the previous conjecture was true, then we would establish a capacity region for these two. Okay, so now that's kind of the meta conjecture. Now the question is, how may these two phenomena be connected? Right? I mean, why would a local imply global, or why would? Again, we have done enough simulations over like last 8 years that we have some intuition on why may these two be connected. And that's the last part of my talk. I mean, that's the last. It's almost one slide. So here is what we observe. So that's presenting as a conjecture. Again, we are interested in maximizing this functional, this non-convex functional. Suppose you have 2 points, alpha is 0 and alpha is 1, which have interior global maximizers. And I'm going to join a path between alpha. So it's just I'm just changing the linear factors in a kind of straight way. Then it seems that there is a continuous path in the simplex such that mu t is the global maximizer of f alpha t for all t. That means that the maximizers kind of move continuously. And if this is true, then you can kind of see why local implies global. Because usually what happens is one of the extreme points, things become nice and convex, so you have this kind of property, and then you kind of keep track of it in a nice way, and you have this kind of property. And so the consequences, so if such a thing is true, and this is what happens in the BEC. So in the BEC, what happens is that in the irrational hyperconductivity, there's a fixed constant distribution that is maximized at some point. Then the maximizer is actually going away from this, but second derivative is 0. So show that to track this, you need to go at higher derivative, like fourth order tail expansion. So you need to do a bit more than to track this, but it does track away. So it does go from here only. It doesn't go away from it. So if this is true, what could you do? You could do plus or minus relative condition implies that local implies global. And you also suppose you want to approximate hyperconductivity, you could start with some nice setting, P goes infinity. And then you would approximate the maximum distribution of the boundary value and decrease P and keep track of it. So it also gives you algorithmically some idea of how to compute things in at least approximate things efficiently. So this is kind of like the conjectures, and that's basically the bigger picture. Okay. I do have a lot of time left, so if there are questions, I can take questions right now, or I can talk about something else related to this. So if there are questions, or we can break up a bit early, but let's. I have a yes. So. Local tensorization, you mean? Yes. The underlying functional. Yes. So you take the local optimizer of the non-convex function. There are many of them. You take the local optimizers here. You take the product distribution of those. You're asking whether there's a local optimizer in the bigger space. Okay. And it's not a priori. Oh, so let me do this test for you for a simple setting to see. You will see something nice. Okay, so let me show you something just to see how you can see. I can raise it too, or I could go there. Maybe. Yeah, maybe. And now you will also see some more. Yeah. So let's look at the following question. Okay. So let's say that you have x, and there is WA of y given x, and WB of z given x. So it's a broadcast channel setting. And looking at the concave envelope with respect to mu x of h of y minus lambda h of z for lambda bigger than or equal to 1. I've just shown you somewhere in the talk that this is subadditive, which means that this satisfies the global tensorization. So I want to test whether it satisfies the local tensorization, right? I mean, just to give an idea of, and this is if and only if. This global tensorization happens only if lambda less than 1 is not true. Okay. So let's test local tensorization. What does it mean? So clearly, if I do, what am I going to do? I'm going to do the following. I want to take a local maximum in the single letter space. So I'm at P of x. I want to test for the local maximum. So I take a perturbation, P epsilon of x is some P of x into 1 plus epsilon L of x. If it's a local maximum, it must be, second derivative must be less than or equal to 0. So if I compute second derivative of h of y minus lambda h of z with respect to epsilon, I get expected value that's what you get. This is, so the second derivative of, I mean, you can see if you are, this is rate efficient information and so on. I mean, there are a lot of links, but I'm hiding all the links, but this is what you get, second derivative. So this, what happens here is that you will get a matrix. So what you will get, if I write this down in a matrix form, it's a quadratic form. So you get like lambda, say b is bigger than it's concave, so it's equal to a. I'm going to call this a. I'm going to call this L transpose. This becomes L transpose AL, L transpose BL. I'm going to call this must be less than this at the local. Okay, now if I take two copies, so I have lambda b1 less than or equal to a1 and lambda b2 less than or equal to a2. Oh, one more thing which I forgot to mention, the first derivative conditions. If I take two first derivative conditions and take the product distribution, that will have the first derivative condition in the product distribution. That's easy. That is just an algebra. So first derivative condition, the only thing you want to check is second derivative condition. So now you're asking whether lambda b1 tensor b2 Kronecker product is less than or equal to a1 tensor. If this is true, then I know that local tensorization is true. Now why is this true? That's easy. Why is this? Let me see if I can. Why is this? I know that a1 is bigger than or equal to b1, I mean lambda b1, and they are all non-negative, PST. So a1 tensor a2 is bigger than or equal to lambda b1 tensor a2, because I'm replacing a1 by a smaller thing, and that's bigger than or equal to lambda squared b1. Now I replace a2 by b2, lambda squared b1 tensor b2. And clearly, because lambda is bigger than 1, is bigger than lambda b1 tensor. And you see, I have used the property that lambda is bigger than 1. If lambda is less than 1, it's no longer true, and this also is no longer true. So there are many, many cases where you see that these two happen for the same set of parameters. Okay, and so there are many, many instances why I think that this is something like this must be true, because you see certain things happening, and that's what I'm saying. I mean, so and for binary Martin also you can actually, it's a bit more complicated form, but you can actually show that this holds. Okay. So what happens is that every local optimizer also has some property, and you can use that property to get some. Okay, other questions? We still have a fair bit of time. Yeah, so what you get, you write the first derivative condition. So this is also same work by Friedgut also did that when you want to do the Brauner-Bechner. He had a proof of Brauner-Bechner. So what you do is you write the first derivative conditions. So there are many variables, but then you see that if it satisfies first derivative conditions, they must have some relationship between the variables. So now you take distributions only over that subspace which has that relationships, and then you look at the function on that. Now it's reparameterized in a much smaller dimensional space. And then you look at those functions, that will have much nicer property. So you will remove a lot of these bad properties and it becomes tractable. You get normally, in our case, we get a single dimensional function. And that's exactly what happens. So that's what I'm saying. So you look at, that contains, so we know that the stationary points must satisfy this. And therefore you take that set of distributions and that gives you something. So that is the idea. And that's, we said it's only a dimensional reduction, right? Because it's non-convex, we need to reduce it to at least, and that's exactly what's happening. And in some sense, okay, there's one more, okay, now I can talk a bit more meta in some sense, because, see, at the end of the day, what do I want to do for this non-convex problem? I want to say that the global maximizer is a product distribution. If you look at things like Gibbs distribution or replica method, things like that, again, you have a non-convex problem. And they want to say that the global maximum, they don't want to identify the global maximum, they want to say there's some nice property. There's some overlap structure which is kind of very nice, or RSB, or so what it seems to be happening is that you may not be able to identify the exact the maximizers, but you should be able to say they lie on a much smaller dimensional space. That's what I really want to say. In this case, so ideally you want to say that you only want for your problem to work that it should lie on a smaller dimensional manifold. And there's the same phenomenon is happening in many cases, right? So you somehow wanted to compress it. And okay, so I told you one problem. Let me tell you another problem, which I don't know. I've been working on this for some time, but it gives you the flavor of problems which I. Oh, this. I have 2 more slides, but I will do this. This is mainly for. Okay, one of the things that started when I started working on this many years ago was the work I did with Varun when Varun was in IIT. So he was a summer intern with me. So we showed this inequality. UV, if UV to X to YZ is Markov, then IUY plus IVZ. When Varun and I showed it for a particular channel, then we generalized it and we wrote a paper together. I mean, with some other people. Let's equal to maximum IXY. This comes from Martin's region calculation. So really, you would think of X as the input, Y and Z as the output, and I'm maximizing over U and V. So if this is and this is saying that if I maximize over all U and V, the optimizer is either U is X and V is a constant, or V equal X and U is a constant. So which means that this problem has at most two maximizers, either at this point or this point. And the way we prove this is by showing that these are only two local maximizers. Okay, so this we can show. There is a source coding dual of this, which is the following: U to X to Y to V is Markov. X and so now you look at when this is just vector plus 2 Z is just X XOR Y. So here this is a conjecture, but this must be true. X and Y binary, and this corresponds setting U equal X, V equal to Y, and this corresponds setting U is V is a constant, say 0. Again, numerically, these are the only two local minimizers. I can't prove it. Even so, I have a similar thing I can prove. I can't prove it here. So the techniques are still very. I don't have the exact thing to prove this. And this is interesting. This comes up in a setting. This is a setting in information theory where you want to look at this expression. And if you have this to be true, then you say that you either do what is known as Steppenwolf coding or Martin coding. So it actually has physical meanings on what is the optimal thing to do. And so what I'm trying to say is that you have these non-convex problems. but the optimizers are very, very simple. Even this, they have, you can guess the optimizers, and they have to be, you don't get some non-trivial things happening. So that is kind of the bigger story, that you have these non-convex problems, and you should be able to say something about this family. It's like linear, and what is the family? The family is alpha as set of x's, essentially, because this can, all of this can be written in terms of entropies of, relativity. So this is not as bad as a generic family. Okay, so that's one other thing. Okay, so now we are almost at a point where it's respectable to kind of stop. So the optimization-based approach have been game changers. So first you went from linear programming to coordinates optimization. There's a whole bunch of things they did, and now I think we are witnessing a jump from convex to specific families and non-convex. They've already made impact they're making impact in machine learning, graphical models, statistical physics, and now I'm saying that even this comes up a lot in communication networks. Okay, so that's basically the story, that we should look at specific families and non-convex where there might be something nice happening. And I think that these two they're all related in some meta theorem. So there's some meta result that's waiting to be found out. And this is not done by me, so there's a lot of people involved in various things. And these are all the various people. Varun is here at some point. Varun was involved. There's Venkat, Varun's advisor, and he works. There's Salman, with whom I worked on reverse hypercontractility. There's Max, who's with Z interference. Abbas, I worked in many settings. Yenlin, with the Gaussian paper, was with Yenlin. Amin was involved with a lot of things. He's very, all the blue people are my PhD students. So that's a color coding. And these are kind of my visitors or associates, research associates, and these were professors a lot much older than me. So that's kind of the age group classification. Okay. Other questions? Yes. One, there are many things. I just don't want. Yes. Yes, it goes there also. So the gray Wiener is source coding. The hypercontractility is same. So I don't really consider, any big difference between channel coding and source coding. It's just that I just focused on some channel coding problems and I have not too many problems, right? So there's similar story in source coding, which I don't have the bandwidth to. I could possibly say the same techniques that you could solve things, but that's not really interesting for me. This is my first thing, right? First, I want to say this because I don't know how to show this. Yes. 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 Input distribution. Yes. 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 So in coarse coding, you can compress like multiple things. You don't do it. So the auxiliaries would generally be a compression of the sources, right? So the same idea comes there. So you have a different, but what you preserve would be slightly different. You don't preserve channel, but you preserve the source distribution. But preserving the source distribution is exactly the same as computing the concave envelope, because concave envelope is preserving, you have to preserve the distribution of source and so on. So the same idea will come through, except that I have not. There are some cases people have done it. People have done something of this form, but they are duals. So yeah, there are a lot of the whole bunch of things. I think there's a. No, they could be. So here is my thing, right? Anything that's not obvious from the material so far would be serious. Anything that's obvious, so I'm more involved in, if I can just plug and play, then that would be right? So it's more techniques involved. So like for here, at the end it may be just plug and play. But I've tried this for a year, and I could get for a lot of things I could prove this, but not for the entire region. Yeah, in some cases it is non-trivial, right? I mean, you could, but some cases I know that there are some, it's immediate. So okay, other questions or comments? You have some questions? No. Okay.
Let's take Chandra Nair. We started with non-convex, we are ending with non-convex, but that's non-convex. And when we enjoy that, and for Wednesday, there is a minus. It's just coming back at yesterday, we will come back at 1:30. So let's make it a little shorter.
No, I made it longer. So it's fine.
So we have 1 hour, 40 minutes rather than 1 hour. Okay. And I think the lunch.
So I had actually at some point I was going to come to see UHK.
Oh, okay.
In quite and with IIT Bombay now.
Oh, okay. So you were visiting SIDS. You were visiting SID. CHK, which is SIDR.
Yeah. So no. So I mean